Electromagnetic waves. The concepts to be studied in this module are Introduction of electromagnetic waves, displacement current, Ampere-Maxwell law, electromagnetic waves, electromagnetic spectrum, a brief recap of the chapter.
Have you ever wondered how an X-rays can reveal great details about the human body? What are the invisible radiations used in radiotherapy known as? How does the food get cooked inside a microwave? How does music reach us through radios, sounds and pictures through televisions, and what carries the signals to and fro from our cell phones? How is communication established through these systems? How are we able to access electronic devices through remote controls and Bluetooth devices? All these applications make use of electromagnetic radiations for their functioning. Let us study this topic to know more about electromagnetic waves. Before studying about displacement current, we should study some laws and views of some scientists to better understand the concept of electromagnetic waves. The Gauss's laws in electricity and magnetism describe how the static fields emanate from charges. Gauss's laws in electrostatics and in magnetostatics are shown on the screen. Faraday's law describes that a time-varying magnetic field or magnetic flux induces an electric field. Ampere's circuital law describes that a magnetic field is produced by an electric current. Maxwell argued that since a changing magnetic field produces an electric field, a changing electric field should also give rise to a magnetic field. Based on the theoretical analysis, Maxwell also predicted that the electric and magnetic fields could exist as self-sustaining electromagnetic waves which could travel even in free space. In 1885, Hertz experimentally verified the existence of electromagnetic waves. Let us consider a parallel plate capacitor connected to a battery through a key. When the key is closed, the current flows in the circuit and the charge begins to accumulate on the plates of the capacitor, which increases the electric field inside the capacitor. During the charging process, if a magnetic needle is placed in between the plates of the capacitor, it shows deflection. Now let us study the case of a closed loop placed between the plates of the capacitor. Consider a closed loop placed between the plates of the capacitor with its plane parallel to the plane of the plates and bounding a surface S. There exists a magnetic field at all points on the closed loop, which in accordance to the Ampere's circuital law is given by the expression shown on the screen.
The application of Ampere's circuital law to determine the magnetic field produced by a charging capacitor seems logically inconsistent. Maxwell pointed out that there should be continuity in the flow of current in the electric circuit, which makes the charging of the capacitor possible. What causes magnetic field between the plates of the capacitors? The source of magnetic field between the plates is the changing electric field. Maxwell named the changing electric field between the plates of the capacitor as displacement current. The electric field between the plates of the capacitor keeps on increasing with time. Once the capacitor is fully charged, the electric field does not change further and the magnetic needle returns to its initial position. The missing term in Ampere's circuital law. Let the area of the plates of the capacitor be A and Q be the charge on its plates at a given instant. The magnitude of the electric field E that exists between the plates of the capacitor at that time, instant, is given by the expression of vector E. Thus, the electric flux linked with the plates of the capacitor will be phi E is equal to Q upon epsilon naught. The rate of change of flux for the small charge dq accumulated in a small time interval dt on the plates of the capacitor is given by d phi E upon dt is equal to 1 upon epsilon naught multiplied by dq by dt. Since dq upon dt is equal to id, therefore id is equal to epsilon naught d phi E by dt. Conclusions drawn from the previous study are shown here. The conduction current and the displacement current may individually be discontinuous, but they possess the continuity through any closed path in a circuit when taken together. The conduction current is equal to the displacement current when they are present in different parts of a circuit. Since in the region between the plates of the capacitor being charged, there is a changing electric field and also a magnetic field, we conclude that a changing electric field gives rise to a magnetic field. Further, as the magnetic field is produced by an electric current, we conclude that a changing electric field gives rise to an electric current, and since this current is not due to conduction of electrons, it is called the displacement current. The electric field is directed perpendicular to the plane of the plates, and the magnetic field generated by it is along the perimeter of the loop. Thus, the two fields are perpendicular to each other. Let's solve a question given here to find the correct option. The correct option is A, that is, by charging the capacitor at the rate of 2.5 into 10 raised to the power 6 volt per second. Let's see its calculation. In order to explain the inconsistency in the Ampere's circuital law, Maxwell performed an experiment to find the magnetic field at a point outside the capacitor by considering different loops. Let's see the experiment performed by Maxwell.
Let us consider a time-varying current I T. Flowing through a parallel plate capacitor C. Let P be the point located outside the parallel plate capacitor where the magnetic field is to be determined. In this arrangement, we will consider 3 cases. Let us study these cases one by one.
In the first case, he considered a point P outside the capacitor and drew a circular loop of radius r touching the point P as shown. Here, plane of the loop is perpendicular to the direction of the current in the wire. Let's see the flow of current through the plates of the capacitor in this case. The magnetic field at small part of the loop is given by the expression shown here. The magnetic field has the same magnitude at all points on the loop and is directed along the tangent to the circumference of the circular loop. On applying Ampere's circuital law, we get B multiplied by 2 pi r is equal to mu naught I t. In the second case, he considered a pot-like surface bounded by the same loop as in case 1. The surface can be considered in 2 parts. Surface S1 enclosed by the closed loop of radius r and surface S2 that lies between the plates of the capacitor with no current passing through it. Let's see the flow of current through the plates of the capacitor and its effect on the two surfaces S1 and S2. In this case, the left-hand side of the Ampere circuital equation is non-zero since a non-vanishing magnetic field exists around a current-carrying wire, but the right-hand side of this equation is 0 since no current flows through the surface S2. In the third case, he considered another surface resembling a box without a lid that is bounded by the loop of radius r. Let this surface have the same perimeter as the pot-like surface considered in case 2. Let's see the flow of current through the plates of the capacitor and its effect in this case. In this case, the left-hand side of the Ampere circuital equation is non-zero since a non-vanishing magnetic field exists around a current-carrying wire, but the right-hand side of this equation is 0 since no current flows through the surface. In the 3 cases, Ampere's circuital law yields different results for the magnitude of magnetic field at the same point P. This is a contradiction which proves the inconsistency in the Ampere's circuital law. Maxwell concluded that not only the conduction current but the time rate of change of electric field is also a source of magnetic field. He proposed that the changing electric field between the plates of the capacitor is equivalent to an electric current known as the displacement current. He pointed out that there should be continuity in the flow of current in an electric circuit containing a capacitor. Therefore, the total current I in the Ampere's circuital law should be the sum of the conduction current IC and the displacement current ID. The modified Ampere's circuital law can be stated mathematically as shown on the screen.
Outside the plates of the capacitor, the displacement current is 0, but the conduction current is not 0. Inside the plates of the capacitor, the conduction current is 0, but the displacement current is not 0. The magnetic field at point M between the plates of the capacitor is same as that at a point P outside the plates.
Although the displacement current is not a current in the literal sense, but it produces the same physical effects as the conduction current. When a steady electric field is generated in a conductor, the conduction current dominates over the displacement current that reduces to 0. Let's study about the consequences of displacement current. The existence of displacement current explains the continuity of current along a closed path in a circuit.
A time-varying electric field gives rise to a time-varying magnetic field, and vice versa. Thus, the electric and magnetic fields regenerate each other.
The concept of displacement current established asymmetry between the laws of electricity and magnetism. Coupled electric and magnetic fields propagate in space in the form of a wave known as an electromagnetic wave. Let's study about the Maxwell's theory of electromagnetism. With the inclusion of displacement current, Maxwell was able to achieve the unification of the laws of electricity, magnetism, and optics.
Maxwell gave the set of equations governing the fundamentals of electricity and magnetism.
Gauss's law in electrostatics stated that the total electric flux passing through any closed surface is equal to 1 upon epsilon naught times the net charge enclosed by the surface. Gauss's law in magnetism stated that the magnetic flux entering any closed surface is always equal to the magnetic flux leaving the closed surface. Faraday's law of electromagnetic induction states that the induced EMF around a closed path is numerically equal to the rate of change of magnetic flux passing through it. Ampere-Maxwell circuital law states that the line integral of the magnetic field around a closed path is equal to mu naught times the sum of conduction current and displacement current threading the surface bounded by that closed path. The most startling consequence of the Maxwell's electromagnetic theory was the existence of electromagnetic waves that consist of time-varying electric and magnetic fields. Here, the electric and magnetic fields vary in time and space but travel with the same frequency. The varying electric and magnetic fields are perpendicular to each other. the varying electric and magnetic fields are perpendicular to the direction of propagation of wave. Unlike mechanical waves, there are waves of matter. Electromagnetic waves are the waves of fields and therefore do not necessarily require a material medium to propagate. The electromagnetic waves can travel not only through air and solid materials but also through vacuum or free space. At any instant, the electric and magnetic fields having sinusoidal variation in time and space can be expressed by the expression shown here. The necessary condition for the production of electromagnetic waves is the existence of time-varying electric and magnetic fields. A stationary point charge produces a static electric field in the space around it. Thus, a stationary charge is a source of an electrostatic field that cannot produce electromagnetic waves. If the point charge begins to move steadily with a velocity v in addition to the electric field, it will produce a magnetic field. But since the magnetic field produced by it is static, a moving charge cannot be a source of electromagnetic waves. However, if the stationary point charge begins to oscillate up and down during a small time interval, its motion will be accelerated. Thus, a changing electric field gives rise to a changing magnetic field. According to Maxwell's hypothesis, the time-varying magnetic field would generate an electric field that would also vary with time. The interaction of the time-varying electric and magnetic fields gives rise to a wave that can propagate through space. Therefore, an oscillating or an accelerated charge produces electromagnetic waves. An electron moving in an orbit around the nucleus in an atom does not radiate electromagnetic waves even though it is accelerated. It is because the electrons revolve in the orbits in which they do not lose energy. Let's see some other sources of electromagnetic waves. AC source connected in a circuit, transition of electrons from a higher energy level to a lower energy level, hot objects, nuclear reactions, etc. Let's watch the following animation for better understanding of electromagnetic waves. Let's study the nature of electromagnetic waves. Consider an electromagnetic wave propagating along the x direction such that the electric field and magnetic field vary along the y and z directions respectively. Here, electric field Ey is equal to E naught sine kx minus omega t and magnetic field Bz is equal to B naught sine kx minus omega t, where k gives the magnitude of wave vector, vector k, omega gives the angular frequency of the wave, and lambda gives the wavelength of the wave. Speed of EM waves in free space is equal to omega upon k, which is equal to nu lambda is equal to c. Thus, velocity of electromagnetic waves in free space is equal to the velocity of light in vacuum. Also, c is equal to 1 upon under root mu naught epsilon naught, where all the symbols have their usual meanings. Thus, it can be said that the velocity of electromagnetic waves in free space is a fundamental constant. Let's study more about electromagnetic waves. They are uncharged, therefore, not deflected by the electric and magnetic fields. They obey the principle of superposition. The optical effects of electromagnetic waves that are visually perceived are due to the electric field vector. For this reason, the vector corresponding to the electric field strength of an electromagnetic wave is known as the light vector. The electric and magnetic fields attain their maxima and minima at the same place and same instant of time. In the shown expression, E0 and B0 are the amplitude of electric and magnetic fields in free space respectively. Let's study about the speed of electromagnetic waves in a medium. In a material medium, the velocity of electromagnetic waves depends only upon the electric and magnetic properties of the medium and is independent of the amplitude of the field vectors, that is, V is equal to 1 upon under root mu into epsilon, where V is the velocity of the wave in medium, mu is the permeability of the medium, and epsilon is the permittivity of the medium. Now let's study about the energy in electromagnetic waves. The electromagnetic waves transport energy associated with moving electric and magnetic fields from one region to the other region in space. The average energy density stored in a static electric field in free space is given by UE, and the average energy density stored in a static magnetic field in free space is given by UB. The electric and magnetic fields associated with electromagnetic waves show sinusoidal variation with space and time. Therefore, E and B must be replaced by their RMS values in equation 1 and 2. Since B RMS square is equal to E RMS square by C square, therefore, UB is equal to 1 upon 2 epsilon naught E RMS square. On comparing equations 3 and 5, we have UB is equal to UE. Thus, the energy carried by the electromagnetic waves is divided equally between its electric and magnetic field vectors. The total average energy density of the electromagnetic wave is given by the expression given here. Let's study about the momentum of electromagnetic waves. Consider an electromagnetic wave propagating with a speed c in free space. If u is the energy of the electromagnetic wave, then its linear momentum is given by P is equal to u divided by c. The sun emits energy in the form of electromagnetic radiations. When we stand in the sunlight, the energy and momentum of the electromagnetic waves gets transferred to us and we feel warm. But why don't we feel any additional pressure due to the radiation when momentum is transferred from electromagnetic waves to us? The reason is that the speed of light is very large. Therefore, the momentum transferred to us is negligible and we do not feel the radiation pressure. The electromagnetic spectrum consists of the following electromagnetic waves. The electromagnetic spectrum is a continuous spectrum in which each distinct type of electromagnetic wave is defined within a range of wavelengths which may overlap in certain regions of the spectrum. Let's study about these waves one by one.
Radio waves are characterized by the longest wavelengths and the lowest frequencies in the electromagnetic spectrum. Its wavelength ranges from 0.3 meter to 600 meter and frequency range from 5 into 10 raised to the power 5 Hz to 10 raised to the power 9 Hz. Radio waves have different bands according to their frequency range.
Microwaves are short wavelength radio waves. They are generated by specialized high-power vacuum tubes, semiconductor devices such as the field effect transistor, FET, tunnel diodes, gun diodes, etc.
Microwaves are used in radar systems for managing air traffic, weather forecasting, and navigation. The common example of microwaves in our daily life is oven, in which microwave radiations of frequency 3 GHz are used for cooking and warming food. Let us study how it works.
The infrared radiation lies between the visible and microwave portions of the electromagnetic spectrum and have wavelengths shorter than microwaves. These are also known as heat waves. Let's study about the sources of infrared radiations. The primary source of infrared radiations is thermal radiations, which are emitted by all hot bodies. When a body gets heated up, its constituent atoms and molecules gain thermal energy and vibrate with greater amplitude. In this process, the energy is released by the vibrating atoms and molecules in the form of infrared radiations. Let's watch an animation to study about very common example of infrared radiations, that is, greenhouse effect.
It is the only region of the electromagnetic spectrum that can be detected by the human eye. It is also known as white light, as it constitutes 7 colors. In the visible spectrum, red light has the highest wavelength, whereas violet has the lowest wavelength. Our eyes are most sensitive to the radiations which lie in the yellow-green range of the visible spectrum. UV radiations are the electromagnetic radiations having shorter wavelengths and higher frequencies than that of the visible light. Welders wear special glass goggles and face masks to protect their eyes from UV rays produced by welding arcs. UV rays are used to kill germs in water purifiers, in LASIK eye surgery, in UV lamps, and many other applications.
X-rays are the electromagnetic radiations having shorter wavelengths and higher frequencies than that of ultraviolet light. The wavelength range and the frequency range of X-rays are given here. These rays are also called Röntgen rays after Wilhelm K. Röntgen, who discovered them in 1895. Since he was unable to determine the nature of the radiation, he named them X-rays, as the symbol X stands for the unknown.
X-rays are generated by the excitation of inner shell electrons of an atom. They are generated due to the rapid deceleration of fast-moving electrons on a metal target of high atomic number. Inside the atoms of the metal target, an inner shell electron is knocked out of the orbit after it absorbs the energy of the incident electrons. An electron from the higher energy level moves to the inner shell to fill up the vacancy created by the removal of an inner shell electron. Since the energy of an electron is greater in the outer shell than the energy permissible for an inner shell electron, it releases the excess energy in the form of X-rays. X-rays are used in different medical applications, like to detect abnormalities, dislocations, and fractures of bones, to detect diseases of the teeth, to locate bullets and other foreign objects within the body, to kill malignant cells that causes tumors and cancer with the help of radiotherapy.
Gamma rays are the electromagnetic radiations having shorter wavelengths and higher frequencies than that of X-rays. Let's take a quick recap of the chapter. Let's recall some important terms related to the chapter. Let's take a quick insight into the chapter.